Okay, hi, this is Daryl Worthy. I'm going to do an example in R on logistic regression. So if you want to follow along, open up the logistic regression underscore example dot R script. So this is what it looks like over here. So we'll be using a data set for this example that has passenger data from the Titanic to examine whether different variables such as age, sex, and passenger class predicted whether the passenger would survive or not. So that's our binomial, binary dependent variable with survival basically on the Titanic. um, so go ahead and set the working directory in line 2 to wherever your Psych671 rstats folder is. So mine's in just on my E drive, Psych671 rstats, and then run line 2. And then run lines 4 and 5 if you have Tidyverse and brms installed already. Those will be the packages we'll use. So not a whole lot of packages. Of course, if you don't have those installed, then you need to type install.package and then in quotes put the name of the package and then let it install and then load the library. Okay, so if you did that successfully, then run lines 8 through 11 to load the data. So this data set called train is what we'll actually use. It's just called train.csv. It should be in your Psych671 rstats folder. So if you have a problem loading it, it's probably that you had a problem setting the current directory as your Psych671 rstats folder. And then what I'll talk about this in a minute, but this test, I also have that, but we're actually not going to use the test data in this example. So there's a header file for the train data. So you can see like passenger ID, survived or not. And then we got passenger class, that'll be one variable we're looking at, age as well as sex. Okay, let's see. So we'll just be using the train data set because survived is not in the test data. So this example was actually based on a machine learning example, which it's up here at the top of the script is the link you can go to if you want to find the full like machine learning example. But here I just kind of took this data set and really just adapted it for logistic regression for this example. So often in machine learning, the data is divided into training and test sets. So this is like a pretty good approach. You basically estimate models on the training data and then see how well they predict data on the test set. But here the regression model is estimated with train, and that's basically what we're going to be looking at. So we're going to be predicting survived, whether they survived or not, are a binary dependent variable from sex, age, and passenger class. So passenger class was like first class through third class, basically. And so third class, what's relevant for this is that the lower classes, especially third, their quarters were like lower in the ship, so they were further from the like the lifeboats, and they may not have even, some of them may not have even heard of like that there was an iceberg that they hit and things like that. So we'll talk. You can look more into Titanic history if you want, but that's just kind of a basic description. So run lines 15 and 16 to run the model. We're just going to be doing a general linear model. Instead of just LM, we use GLM to denote that we're using the general linear model instead of just a linear model, which just assumes a Gaussian or normally distributed continuous dependent variable. But here we use family binomial to declare that our outcome variable is just a binary value. Okay, so we run that and we get these results right here. I've pasted them over here in the PowerPoint. Okay, so Gaussian is the family of distributions we assume with a continuous dependent variable. So we have to change that to binomial in this case because we have a binary dependent variable. So we can look at the null deviance. So it gives us like the null deviance as well as the residual deviance right here. So that's like the model deviance. And we could compute McFadden's pseudo R squared just manually from this. So another way to write the equation for pseudo R squared is 1 minus the deviance for the model divided by the deviance for the null. So the ratio of the deviance for the model divided by the deviance for the null. And then since lower values are like better when we're talking about log likelihood, that's like an error term, we take 1 minus that basically. So run line 18 to compute it. Deviance and null deviance are objects within the fit object. So we got those from M1 right here. M1, so you can get that like just by typing N1, that's our fit object, and then we could type in deviance, and so we can see that we get that right here, residual deviance. And then the same thing we get, it also can provide null deviance. So we run that right here, okay, and then there is our McFadden's pseudo R squared, so 0.329 basically, okay. So we can see that the coefficients for all three predictors are significant up here. So passenger class significantly predicts survival rate, sex predicts survival rate, and age does as well. And of course, these are simultaneously regressed, so they predict unique variance in survival rate, even after accounting for the other variables included. So you can take the coefficients. So this coefficient function can be applied to these model fit objects. And so we can type in coefficients, and it'll just give us the coefficients right here. Okay, but we can run line 20 to get our odds ratios. So remember, these coefficients are all in logits or log odds form. And so we want to interpret them in odds form. So to do that, we raise the coefficients, or we raise e to the power of the coefficients using the exponential function. Okay, so if you run line 20, this will give us odds ratios. And you can see that these are all negative. So as passenger class increases, so basically going down in passenger class from first to third class, the odds of survival decrease. So first class passengers were more likely to survive than say third class passenger. As passengers go from female to male, their odds of surviving decrease. And as their age increases, their odds of surviving also decrease. Okay, so we can run line 23 to get 95% confidence intervals for the odds ratios. Okay, so we run line 23. It gives us our odds ratio right here. Those are the coefficients. And then the confidence intervals for M1 exponentiated again, because we put this all within the exponential function. We get those right here. Okay, so you can see that those are all different from 0 basically, and they're all distinct from 1 as well. So we can see that the odds ratios are less than 1 for each of the predictors. As passenger class increases from first to third, the odds of surviving are multiplied by 0.27, meaning they decrease. The odds for male surviving are given by multiplying the female odds by 0.08, so they decrease substantially. And then as age increases by 1 unit, the odds of surviving decrease by 0.96, or multiplied by 0.96. So it's easier to think of odds greater than 1 than less than 1. So an odds ratio of 10, for example, means like something is 10 times more likely given the data. So we can run line 27 over here to transform the odds to the reverse. Okay, so transform the odds to the reverse. Now you can think of these as the odds for like lower values, or the odds for females surviving compared to males. Okay, the odds of with decreases in age leading to survival. Okay, so a 1 unit decrease in passenger class, so going from like third class to second class, to first class. Those are really kind of increases in class, say, but the way it's enumerated, it's a lower number. So a 1 unit decrease in passenger class translates to a 3.63 increase likelihood of surviving. So you were more likely to survive if you were second than in third, and then if you were in first than in second class. And we'll look more closely at these effects in a little bit. Females were 12.45 times more likely to survive than males. And then as age decreased, the odds of surviving were multiplied by 1.04. So this one, if we think about like what caused these effects, passenger class, there's probably different reasons in these last two. These last two are probably, caused by women and children first, that being like the predominant heuristic then, whereas passenger class is probably that the higher passenger classes, first and second, were near the top of the ship, closer to the lifeboats, and closer to like getting off. Okay, we could also just reverse code survived as perished, or we could say like died if we wanted to. So run line 30 to use an if-else statement to create the new variable. So basically we're using this if-else statement. If train survived equals 1, we're going to change it to 0. So basically now, if you survived, you're going to get a 0 for perished. And if you didn't survive, if it doesn't equal 1, this is the else part, then you get a 1. So if you did not survive, you perished, you get a 1. So now we've added this new variable perish to the data set. And when we run it, we can see here. And survived is like up here for each person. So these will just be basically the opposite, because that's how we did it. Now let's run lines 33 through 34 to run the model with perished as the dependent variable. Okay, so get our summary. So this will all, be basically the same. It won't change like the model fit or anything like that, but it'll change the coefficient values. So now these coefficients are positive, meaning like passenger class had a positive relationship with perishing. Males were more likely to perish. Again, these are in logits right here, so we haven't transformed them to odds ratios yet. And then as age increased, there was a positive effect on perishing. So run line 37 to get the odds ratios. Okay, and so we get the odds ratios right here. We kind of, computed these the same way above, but now we did it again by just reformatting the outcome variable. Okay, so we can see that they're the same as when we took the 1 minus the odds ratios for the model with survived as a dependent variable. So we could think of it as males, older passengers, and people in second or third class being more likely to perish rather than less likely to survive. It's just the way, we frame the dependent variable. So to look more into this, and maybe, if we were publishing this, we would want to kind of plot some of these results. So now let's plot our data and use stat smooth to plot the logistic regression curves. So run lines 41 through 46. So this is right here. It uses a lowest function to plot the probability of surviving as a function of age separately for males and females. Okay, so here I've plotted that. Okay, so in our aesthetics right here, we named the data frame. Then aesthetics age is X, as numeric survived is Y, and then color equals males versus females. Okay, and then stat smooth lowest, formula y equals x, and then the color tells it to plot these differently. And then we can also plot in the actual points if we want, so using this geom point value, and then finally we add labels for x, age, and y, probability of surviving. Okay, so we can see some interesting effects here. So for females, it actually was a little bit higher for older females' probability of surviving. Whereas for males, you can see that the kids had a decent chance of surviving, but then it drastically fell for the men, basically. So they, didn't, not as many of them were allowed on the lifeboats. So run lines 49 through 54, so plot 2, to create the same plot with passenger class on the x-axis, and then still plotting separately for males versus females. Okay, so here's passenger class. So you can see that if males were first class, they were more likely to survive. But then if they were second or third class, it was a very low probability of surviving. Okay, but then if females were first or second class, they had a very high rate of surviving. But if they were third class, they had just about a 50-50 chance of surviving. So now run lines 57 through 70. This will create plots with method equals GLM. So a lot of this is the same, just the method is slightly different. Okay, method arguments, we have to list it as binomial rather than as a lowest function. So this one, you'd probably want to use this maybe in your paper because this actually shows like the relationship that was estimated using the binomial logistic regression model. So here's this first plot right here. Okay, so that was like plot 1A. So looking at the effects of age, separate for males versus females. And then same thing, but with passenger class. So really just the same plots we created up here with P1 and P2, but now instead of using a lowest function, we use the GLM to create like a smoothing function. So now let's run lines 73 through 79 to plot probability survived by age separately for each passenger class. And then we're using males versus females. So this will have basically all of the data that, it'll show kind of all of the results pretty much. Okay, because we have the relationships between age and survival, and then separately within each passenger class, first class, second class, and third class. So all I did was I took plot 1A right up here, and I used facet grid. So this is a useful function. Facet wrap is also similar. So facet grid by passenger class. And so it creates separate subplots of this plot right here, but for each passenger class. So really, I think it's a really interesting and useful feature for ggplot. Okay, so over here, like passenger class third, overall not many surviving, but still effects for age and sex. Okay, and then effects for age and sex over here, but we can see like for classes 1 and 2, like females basically had a pretty good chance of surviving. Okay, so we could look at this data. We might think like, well, classes 1 and 2 look pretty similar and dissimilar from class 3. So we could use like factor to declare passenger class as a factor. Here we've treated it as numerical, but we'll kind of stop here. If you were actually publishing this, you might look into like this further. You could test possible interactions and things like that. But here we're really just kind of interested in looking at a simple logistic regression example. So you can also run lines 82 and 83 using brms. So I'll go ahead and start that running. It'll take just a minute. Okay, so one thing to note about brms is everything is about the same as it would be if we were using like a continuous dependent variable. But instead of family, which is assumed to be Gaussian or normal, we have to declare the family to be Bernoulli. So Bernoulli is the conjugate prior of the binomial distribution. And so it basically kind of means the same thing as the binomial distribution. So we just use Bernoulli when we use BRM, whereas for GLM above, we declare the family binomial. Okay, so it's finished. So it ran it, probably in less than a minute. This isn't a multi-level model. It's just a regular regression model. So it usually runs these fairly quickly. Okay, so the coefficient estimates are similar to when we used the GLM. So again, these are in log odds. So negative values imply negative relationships, but it's hard to interpret that metric. And then, of course, again with BRMS, when we perform inference, we're interested in whether the credible interval includes 0. And so all of these bounds are outside of 0. They're all negative. And so all of these are significant, which we already inferred up above just using GLM. Okay, you can run lines 85 through 87. Okay, so here's our fixed effects for B1. Okay, so it'll show the odds ratios. So once we run line 87, it'll show the odds ratios basically. Okay, so the odds ratios here given just from our BRMS output. And these are all pretty similar as what we got in the earlier output. Okay, run line 89 to take the inverse odds ratios and describe them in the opposite direction. So if we were trying to look at the probability of dying, basically, this is what kind of we looked at earlier. Increases the odds of not surviving or perishing. So we can see that these are similar to the odds ratios we got using GLM. So 0.006 for the intercept, 3.663, just a little bit different for passenger class, 12.45 versus 12.72, and 1.037 the same for age. Okay, so pretty similar, but they'll be slightly different because BRMS analyzes in a Bayesian format. Okay, finally, you can run line 91 to plot the conditional effects and hit return to see each plot. Okay, oh, is it doing it? Oh, my R session died. Okay, well, luckily that's about the end of this. So R does that from now and then, so I would just start a new session, but this is the end anyway. Okay, so you could plot those conditional effects. Okay, so for the last thing for this short lecture, let's do a JASP example. So let's do the same, basically the same data, but using JASP. So open up JASP. So here I have it open already. And then open the train.csv dataset. So train.csv, I've already opened that right here. Click on regression. And then logistic regression, which I'm kind of already in over here. And then enter survived as the dependent variable. And passenger class and age as covariates. And then enter sex as a factor. Okay, so let's first, so we can see the output that we get over here. Here's the coefficients and our model summary that we'll talk about in just a minute. So let's first compare the coefficients that we got in R. So these are them right here. We can see that we get basically the same thing in R. Age is just listed fourth in R, whereas it was third over here. I'm not sure why. Oh, it's because we entered it third, and then the sex is the factor. So now let's look at the model statistics. So this is just reprinted down here below. McFadden's pseudo R squared is the same as what we computed in R. So 0.329 and 0.329 there. AIC, that's Akaike's information criterion, AIKE. So that was a paper in the 70s. Basically, these are model comparison metrics that account for the differences in the number of free parameters. So there's more free parameters in H1 than in the null model. There's 4 additional parameters. Okay, and then BIC is just another transformation of deviance by penalizing by the natural log times the number of observations times the number of parameters. So AIC and BIC will be larger the more free parameters you have. But we have such a huge difference in deviance that the null model definitely is not a better model than H1. So we can see that degrees of freedom equals 713 for the null model. So there are 714 observations. In R, you can type log of 714. Okay, so log of 714 equals 6.57. So this is the difference between BIC for the null model and its deviance. Okay, so for the null model and its deviance, it has one parameter, the intercept. Okay, so it penalizes by that value, the log of 714 times the number of free parameters, which is just 1. Okay, so it adds 6.72 or 6.57 from the deviance to get BIC. And then for H1, there are 4 parameters, so the intercept, and then sex, age, and passenger class. Okay, so we take log of 714 times the number of free parameters. That gets us 26.83. And then the difference between BIC, 673.574, and deviance is equal to that difference right there. So that's how BIC is computed. So BIC and AIC you will probably see, a lot, particularly if you do, any high level statistics, because they're metrics that are used a lot when you're estimating things through log likelihood. So Wagon Makers published a paper in 2007 that I think is a really good methods paper. Talks about the limits of p-values and how we could use like BIC basically to compare a lot of models and get Bayes factors other than p-values. So it gives a method to compute a Bayes factor for the odds that one model is better than the other given the data, or provides a better fit to the data than the other. So specifically, the Bayes factor in favor of model 1 over model 0, so say the alternate model over the null model, is equal to the exponential of 0.5 times the difference in BIC between the null model and the alternative model. So the null model will usually have a higher BIC than the alternative model. We can see that's definitely the case here, 971 versus 673. If you plug these values into R, like I did right here, okay, we get an extremely high Bayes factor, so e to the 64th power. So that's extreme support supporting M1 over 0. Basically, a BIC difference of about 12 indicates like strong support for one model over the other. Okay, so we can see like if we put exponential of 0.5 times 12, say that's the difference in BIC, that gives like extreme evidence. I think maybe it's actually 10. Let's see if it's 10. Yeah, so still pretty extreme evidence. Okay, so now click on statistics and check odds ratios. So that's over in JASP. So I actually haven't done that yet. So click odds ratios. It'll give me the odds ratios and 95% confidence intervals for odds ratios. Okay, so here are my 95% confidence intervals for odds ratios. Here are the odds ratios right here. Okay, actually, these are 95% confidence intervals for just odds. Yeah, I think if we put odds ratios, yeah. So if you check odds ratio scale, then it will give you the confidence intervals for odds ratios. Okay, so 95% confidence intervals are computed slightly different than in R. I am not exactly sure why, so that's just something that I do not know, but there's probably a reason. They're really just small discrepancies though. So there are odds ratios for each of these effects. And of course, if we wanted to like recode this as perish instead of survive, then we could do that and then run these same results. Now under plots, so plots check display conditional estimate plots and show data points. So I haven't done this yet either, so we'll see if it's here. So display conditional estimate plots, show data points. Okay, and I get these plots right here. So I've reprinted them over here. So you can see probability of survived equals 1, goes down with passenger class, goes down with age, and then goes down from females to males. So that's kind of it for this example, but here are a couple of additional examples if you want to look into this more. So another logistic regression example out of UCLA. They have a lot of good stats examples, but this one predicts grad school admittance from GRE, GPA, and rank of undergraduate institution. So like probability of being admitted into grad school, that's like a binary outcome. You're either admitted or you're not. And then this one is a multinomial logistic regression. Predict academic program that participants or people would enter into, and there were 3 different choices from one's socioeconomic status and their writing score. Okay, and this is again one from UCLA. But yeah, there was a question about multinomial logistic regression in the last class, and so yeah, that's a perfectly valid technique. And so here's an example if you want to learn more about that. Okay, that's it for this lecture. Hopefully this has been informative on using logistic regression in R, and I definitely encourage you to try to replicate all of these results yourself. It should be pretty simple and straightforward. Okay, that's it.